Okay, all right. Okay, so just acknowledge once that everything is visible and I'm audible and the screen is also visible. Everything's fine? Okay, if anyone of you can acknowledge yes or no or anything else.
Yes, sir.
All right, fine, thank you. So let's get started with today's session. It'll be a brief session today, maybe one and a half hour session. So what we are going to cover today is MOS electrostatics. And as per the protocols, we need to introduce ourselves. And I'm Shahzad Bhatt from IIT Bombay. I'm working in electrical engineering department, and this is Introduction to Semiconductor Fundamentals course offered by IIT Edge, which for which the instructor is Professor Naresh Kumar Imani. What we are going to cover today is MOS electrostatics, and we are going to see where it's going to play the role in the devices and what are the things you have already covered and where you are going to use them in the future and where we are heading towards in this particular course. So, as per the my ritual kind of, I like to start with the basics, whatever we have covered till now and where we are heading towards. And I have been emphasizing this point again and again in my sessions that if you have that framework in your mind that where you started and where you ended in the course, you can just map anything, you can just link anything in that course. That you start from point A and ended at point B, and you will be able to comprehend the other complicated things by kind of framing that map in your mind. So let's briefly talk about maybe 10-20 minutes about what we have covered till now and where we are heading towards, and just a brief introduction to uh, whatever has been covered till now, and then we will then we will jump to the questions which are covered in the assignment problems. So let me just add a few pages here so that we can get started. Okay, all right. So let's get started. Just a brief revision, recap. So from lecture first to lecture, I guess this is eighth, or I should say the week eight. So what we have covered is that we started fundamentally with the atomic picture, considering its potential, just like a hydrogen atom, and we said that its potential is something like kq over r. Okay, so where r is the distance between the two charges, let's say the electron and the nucleus, then we say that if we have a bunch of atoms, let's say in a solid, where they are repeated over a certain distance, where this distance between the two atoms is something called as lattice constant. This makes up a region where you have these repeating potential wells, repeating potentials, and you convert them into using certain approximation, you consider them as a square potentials, and then using the concept of Bloch's theorem, which uses the concept of periodicity of the wave function, and it says that if you know the wave function here, then you can compute the wave function at this position. There may be certain phase factor associated with that wave function. Okay, but because of the periodicity of the lattice, you invoke something called as Bloch's theorem in what you call as chronic penny model. This is basically the chronic penny model where you consider these square potentials, repeating potentials. Okay, what you get is from the chronic penny model, when you solve it, you get a picture where you get energy versus the k vector of an electron, how it behaves inside a solid. So because of n number of atoms present inside the solid, so there will be certain energy values of the electron which will be allowed because of its wave nature, and certain values which will not be allowed by the crystal. So it is purely a property of a crystal that it allows certain energy values of the electron, and it does not allow certain energy values of the electron. Just like if you have a waves, if you have some waves going like this and another wave going like this, then these waves can interfere, and that interfere can create certain regions where you have the maximum amplitude and certain regions where you have the minimum amplitude. That means certain regions where there are allowed values and certain regions where there are not allowed values, just like these, just like interference of the two waves. Okay, because there are many multiple electrons present inside the lattice. And what this picture gave you is something called as a band structure. Okay, where you say this is the energy axis, this is the K axis, and you get these allowed values of energies. Okay, so the when you solve the chronic penny model, you get an implicit equation which you can solve either numerically or you can solve it graphically. So we prefer to solve it graphically here by plotting the right hand side and by plotting the right hand side and the left hand side of that equation, which you have covered in the initial lectures. The right hand side consists of some sine hyperbolic terms. The left hand side consists of some cos k terms. The cos k sets the values of this on a graph to be between +1 and -1, because cos varies between +1 and -1. And the right hand side is some sine hyperbolic functions, which when you plot gives you something like this. And then there you say that these particular values which are between +1 and -1 are the allowed values. Okay, these are the allowed values. And the one shown in this magenta color are not allowed values. And then you map it onto this particular figure. These particular bands are these allowed values, and in between you have these particular values which are not allowed. So these are not allowed values in between, which is basically called as band gap. And then you go on and you basically see that there are bands of these. Okay, and you basically get a picture which looks something like this. So you have bands of allowed energy values. This is the extended zone representation. Extended zone representation. This is E versus K. And when you fold it into a single zone, this particular zone, you fold these energy bands back into this first zone, which is called as first Brillouin zone. When you fold it back, you get a reduced zone representation. You get a reduced zone representation, something which looks like E versus K. This is the allowed value, this is the allowed value, and then it folds back here, and these fold back here, and you go on and on. Okay, so these are the allowed values of energies now, which are folded back into the first Brillouin zone. Okay, and we study this first Brillouin zone, and because of the periodicity, we consider that whatever is happening in the first Brillouin zone is happening in other part or other unit cell. Okay, so that is the concept of the Brillouin zone, and this particular point is called as the gamma point. This particular point is called as X point. So these are related to different Miller indices in the lattice. Let's say you have a lattice system like this. This is the lattice system, maybe these hexagonal cells. Then if you consider this particular point here, this can be considered as gamma point, this can be considered as X point, maybe M point or other points, and this is the particular Miller indices direction. So these are the directional coordinates on the three-dimensional crystal systems, along which you measure the acceptable energy values of electrons, because electron is living in a three-dimensional system. So right now we are talking about three-dimensional systems here, okay, not any 2D materials or anything. So electron has to move in a three-dimensional crystal, so it will face some allowed values and some unallowed values. So that is the particular representation which is shown by the reduced zone representation, and you get these particular energy band gaps. And what you do is that you then call this particular level as the bottom of this particular band as conduction band, the maximum of this band as valence band, and you get this particular picture of a conduction band and a valence band. Okay, you get this picture of a conduction band and the valence band. and mostly you are associated with the values which are near to the parabolic minima, near to this particular point where k vector almost stays approximately as zero, because most of the electrons are located or localized in this particular region when we are considering very low excitation regime, or mostly the conduction takes place because of those electrons. Then you map those electrons into something called as band diagram, and you make the energy versus the space coordinate, where you call this as conduction band, you call this as valence band. And whenever you have to deal with, let's say, vacant space, you deal with the vacant space in the valence band, you deal with the full, I should say, the electrons in the conduction band. So basically, whenever the conduction takes place, these are the occupied states. Whenever the electron goes from this particular state to this particular state, there's a vacancy created. This electron goes here, the vacancy moves here, and it keeps on propagating by the application of the electric field. Okay, just clear this concept in your mind. So that's why we use the notion of hole propagation in the valence band and the electron propagation in the conduction band. Okay, it's just the notion we have kind of used to understand the conduction mechanisms. And this is also true in case of metals also. Although we do not usually talk about electrons and holes in a metal, but this is also true in metals. So it's a universal concept of using the electron and hole picture. And what happens now is that uh, when you take a, for example, a semiconductor chunk, semiconductor bar, let's say of intrinsic type, you get this particular system where there is a conduction band, when there is a valence band, and there is an intrinsic energy level, which is the Fermi level of that particular system in equilibrium. Okay, then you particularly take another this particular piece of semiconductor and you dope it. Let's say you dope it with maybe Nd or Na, acceptor type or acceptor type impurities or donor type impurities. These are the group 5 elements, and group 5 elements, these are the group 3 elements. And this particular thing has extra electron, and this particular thing has extra hole. Okay, so you represent this particular thing as when you let's say dope this particular side as Na, you dope this particular side as Nd, you get to a structure where you have, let's say, a P on this side and N on this side, and there is a space charge space charge region formed between the P and N, and you have a positive charge and extra electron here, negative charge and extra hole here. And that's why this particular region is formed, because excess electrons, because of the difference in Fermi level, when the contact is made, these electrons want to go here, the hole wants to go here, and it leaves behind these positive charges. Though these are the positive charges which actually get kind of accumulated in this region, depletion region. Okay, so this is the depletion region. And now from this picture, you move on to applying the bias to this particular system, applying the bias. And you saw that when you apply a positive bias, what happens when you apply a negative bias? You call this as forward bias if the higher potential, higher potential is connected to P side. This is important. It's not always that positive is connected to P side and negative is connected to N side. Higher potential should be connected to the P side and the lower potential should be connected to the N side. That is the actual kind of key concept in this particular picture. People try to trick you by using different potentials, and then kind of some maybe most of the students make mistake. They find where is the positive and where is the negative. The key concept is that higher potential should be connected to the positive to the P side, and the lower potential should be connected to the N side. So you call this as forward bias. And if the lower potential is connected to the N side, you call this as reverse bias condition. And you saw that under forward bias condition, there is huge current and current flow, and you get a diode in a on state. So there's a current flow and you get something like this. These are the bands where there is a separation of the Fermi level, and this separation of the Fermi level is basically Q times V applied bias. And then you saw that the electron, because of the electron distribution on this side, these electrons above this particular level, they can go on this side, and this helps in the conduction. And similarly, in the reverse bias case, you saw that there is a huge barrier. The Fermi levels are somewhat like this, and the electrons are not able to conduct, except there are certain non-ideal conditions where the tunneling and other things come into picture, or something called as field ionization, impact ionization can take place. But in a reverse bias, we consider that almost negligible current flows, which is something called as reverse saturation current. And that's why you get an IV characteristic, the diode current versus the voltage, as something like this. If someone has any question, you can just mute yourself. Okay, so you get, this is something called as cut-in voltage, and under in the reverse bias case, this is the reverse saturation current. And moving on quickly, then what you covered is basically the electrostatics part, where you basically studied about the drift, where you studied about this is basically carrier electrostatics. You studied about the diffusion, you studied about the Poisson equation, and after that, you basically moved into a system where you have a metal and semiconductors. And why this is important? Because in the end, you have to make a contact with the semiconductor, and that contact is mostly made with the metal. Whatever you connect with the semiconductor to retrieve the currents, to connect it to the circuits. Okay. So you studied about the Schottky barriers or Schottky junctions. You studied about the ohmic contacts. You studied about Schottky barriers of two types, which is the ohmic, and the another is the rectifying behavior. Okay. So here you studied what happens when the semiconductor is n-type, and what happens when it's p-type, what happens when this is n-type, when this is p-type. Okay, so you study that whenever the contact is made, you get a barrier between a metal and a semiconductor, something like this, where this is a semiconductor, where this is the Fermi level of a metal, and you have a barrier here formed, which is something called a Schottky barrier. Okay, and this particular thing can be considered. This is considered as it's like a surface potential. It's like a potential at the particular surface. But that's what we are going to deal today. Now you studied about the metal semiconductor junction. Then you moved and transitioned into what happens when you place an oxide between the metal and the semiconductor. This is the oxide, metal oxide semiconductor. Now this particular picture changed. How it changed, that's what we are going to see today. So we are going to study the electrostatics of this particular system, and I hope I'm audible because I can see this particular video is stuck here. Okay. Okay, so what you're going to study today is that the electrostatics of this particular MOS system. So what happens when you place an oxide? Earlier you had a metal, you had a semiconductor on this particular side. This was the Fermi level of the metal. This was the, let's say, the conduction band of the semiconductor. Let me draw it like this. And this was the valence band of the semiconductor. Let's consider this as initially n-type, and this is the Fermi level of the semiconductor on this side. Now, earlier what you did is that you made the contact, and what you got was a barrier, which was the Schottky barrier. Okay, Schottky barrier. Now the scenario has changed. Now you have to consider the oxide in between the metal and the semiconductor. How is that going to affect the band diagram? That's what we're going to see. Let's say you have a MOS structure. You have MOS structure where this particular thing is an oxide. Then you have the Fermi level for the metal, which you can say the conduction band for the metal. It's one and the same thing. And for the oxide, you have a conduction band like this. This is the conduction band of oxide. This is the valence band of oxide. So it is so huge that the energy gap of the oxide is approximately 9 electron volt for silicon dioxide. But for most of the oxides, the energy gap is huge. That means at room temperature, there are no free electrons present in the system. I should say zero free electrons, because for the electron to go from valence to conduction band, it requires huge energy of the order of 9 electron volts. So there are no electrons in this particular system. That's why it's oxide. Okay. Now for the semiconductor, you have a conduction band you have you have a valence band, and let's say if you consider this as n-type semiconductor for time being, then this is the Fermi level of this particular semiconductor. Now what happens is that when you this was when all of them are separate, not combined. Okay, and you consider a common level of the energy, which is the vacuum level, which is the energy which is required to kind of make the electrons totally free from the force present inside the crystal. Okay, so this particular energy difference is called as the work function of a metal. It is the energy required to make the electrons totally free, I should say. Okay, just a crude definition. There is a deeper explanation of what the vacuum level is, but just for a basic understanding what it is. And this particular thing is called as the work function of a semiconductor, where the difference between the vacuum and conduction band is called as something called as electron affinity. The difference between the vacuum and the valence is called as ionization potential. We don't mainly deal with it because it takes huge energy to directly excite the electrons from valence to the vacuum level. Mostly they are, this is the job of a very, I should say, the high energy particle physics people. So let's not go into that. So what happens when you combine it? So when you combine these particular semiconducting systems, you know from the basics that you should be having a common Fermi level in the system because this is going to behave as single system now. Okay, so now if the Fermi level is going to be common, that means there has to be some band bending somewhere else in the system. Okay, or maybe that may be compensated by something else. So when the Fermi level is common, let's say you have the Fermi level in the metal, then you have the oxide. There is also a Fermi level in the oxide. Let's consider it in between of the oxide band gap. You have a conduction band like this, you have a valence band like this. Conduction band, a valence band, and this all is flat. This is called as something called as, I should say, all of the bands are flat right now, and this is something called as flat band condition, where there is no band bending present inside it. And because the Fermi level wants to be aligned, because all of the bands want to be aligned, so this is the ideal situation when we are not considering any, let's say, charges inside of the oxide. The oxide is free of any charges. So everything wants to be aligned in the equilibrium state, equilibrium position. Now what happens is that now you play with this particular system. The vacuum level stays like this particular. Okay, now you play with the system. How you play with the system? You apply the biases. You apply the positive bias. You apply the negative bias. You increase the negative bias, and you see what happens in the system. Okay. So first, what happens when you apply a positive bias to the system? When you apply a positive bias here and negative bias here, negative is going to raise the electrostatic potential energy on this side for the electrons, and positive is going to lower the electrostatic energy of the electrons on this side. So accordingly, the bands will bend. What is going to happen now is that the Fermi level on the metal will drop, and the Fermi level on the, I should say, the semiconductor is going to raise because you have applied positive here, you have applied negative here. Okay, the oxide is going to, let's say, stay like this. Whatever happens in the conduction band and valence band of the oxide, we are going to see. There is also a bending in that particular region, but let's draw it like this particular for the time being. Then what happens basically is that the bulk stays like the n-type. There is no change in the bulk. That means this particular distance remains same even if you apply the bias for the positive bias. Okay, this is right now the positive bias. And this particular thing again remains the same. This is the conduction band, this is the valence band, this is the Fermi level. Now, because you have applied the negative bias here on this side, this particular thing starts to bend just next to the oxide. Okay, so there is this particular band bending, as a result of which this same bending gets reflected in the oxide bands. And you know from the PN junction concepts that this particular bending, when there is a bending in the depletion region of the PN junction, the slope of this particular thing gives you the electric field basically. Okay, so the electric field is directly proportional to the slope of this conduction band. So you know this is from the basic electrostatics. And it also gives you the direction as well. So this is from the basic electrostatics, you know. So that's why you know that whenever there's a bending at this particular region, there is a bending, it indicates there is something, I should say, the electric field present. So the electric field, this particular slope tells you about the electric field present inside this particular system, which is the which is the electric field developed at this particular interface. I think there is some lag with this system. What is happening? Is there any lag between my writing, voice, and the video or anything? Hello? Can anybody just acknowledge? Okay, because I can see that there is some lag between the writing and the audio, I guess. If you can acknowledge, I may be able to rectify this error because I don't want it to get propagated in the entire session. Anyone there to acknowledge? Okay, let's see. Okay, so let me just continue. Maybe it would be rectified by its own.
What you say now, I can understand, sir.
No, no, I'm saying that is there any delay between my writing and the voice?
No, sir.
Okay, fine. Thank you for acknowledging. Okay, so what is going to happen is that now there is a region formed here in this particular area, and there is a bending also. And you had that intrinsic level before, which is something like this, that also bends down near the oxide. So what does it mean is that near this particular region, if there are, let's say, the positive charges here and there are electrons here, so if electrons can easily stay at this particular region because the electrostatic potential at this particular region is lower as compared to that of the bulk. So that's what the band bending basically tells you. Okay. Now, what happens is that if you just, for example, go on increasing the if you just reverse the polarity of this particular bias you have applied, what you are going to do is that you're going to reverse the bending. Okay, and then you are going to have the regions of depletion, you're going to have the regions of accumulation. We're going to talk about this briefly, and you are going to have inversion. And then there is one more region called as strong inversion. You can control these regions by controlling the bias. How? First of all, let's talk about depletion. What happens in a depletion? In depletion, the surface gets depleted of the electrons, of the carriers, basically. What do I mean by the surface gets depleted by the carriers? So let's say you have a oxide and you have bending like this in a system. Okay, and you have the let's call this the Fermi level of this particular system, and let's call this as intrinsic level. Okay, intrinsic level. This is intrinsic level. This is Fermi level. This is conduction band. This is valence band. And considering this, let's say this is the Fermi level of the metal. So in this particular scenario, you see that you have applied a negative voltage here. Okay, that has raised the Fermi level from the metal side because electrostatic potential energy raised due to the application of negative potential. And the difference between this Fermi level and the Fermi level of this particular semiconductor gives you the applied voltage, Q times V applied. Just a similar concept as that of the PN diode. The difference of the Fermi levels. Okay, now what happens is that you see that this particular region intrinsic level touches the Fermi level at the particular surface at this particular region. It means that this particular region near the surface, it has become p-type rather than n-type. But inside the bulk here, it is n-type. This is the bulk of this, and this is the surface near the oxide. Okay, that's what band bending gives you the information about. That the band bending is telling you that here it has remained n-type, whatever what it was before. But here it has almost just like a p-type behavior because the Fermi level is now closer to the, I should say, valence band here. Okay, if you see this particular difference and if you see this difference, this one is lower. Okay, this particular difference is lower than this particular difference. Okay, so that's why the Fermi
Yes,
level is
yes.
closer to the valence band, and you get depleted charges here, which are the positive ions. Okay, because you have depleted those ions by applying the positive voltage here and negative voltage here. All those electrons you have taken out from the system and deposited over here on the metallic side. And you have, because you know on the n type, on the n side of the semiconductor, you had a positive and a excess electrons. So you take away these electrons. Whatever remains is this particular depletion charge. So that's why when you show the space charge region, looking at the page, when you show the space charge of this particular system, let's draw the space charge diagram. This particular axis is the charge per centimeter cube, and this particular is the x. When you do it, you show this as something like a step, the positive charge, which are the positive ionized, I should say, the donor atoms. Okay, it's similar to that of what happens in a p-n junction. You draw the space charge here as this, except in the metallic side you don't have these negative immobile ions because metal is full of free electrons. You don't get a immobile ion in the metal because the initial, whenever you apply a certain electric field or whenever you apply any sort of field to the metal, electrons are the first thing that respond because it is full of free electrons. It's full of something called as free electrons C. That's not the case in the semiconductors or insulators or the dielectrics. That's the difference between the metals and the semiconductors. So what happens is that you get this particular space charge. This is in depletion. That's why this regime is called as depletion because you have depleted the region near the oxide and semiconductor. And on this particular side, you get negative charges, which are the free electrons, and you showed them as a delta function because they are mostly, I should say, the mostly localized first near the metal oxide interface, and there are so many number of electrons present in the metal that instantaneously form a kind of a delta function near the oxide whenever you apply a field. They are the ones to respond. Okay, but in the semiconductors there are not as excess electrons as in the metal. So that's why you deplete the semiconductor. The remaining things are the ions. They get settled there. You call that as, this is called as depletion region now. This is the depletion region, and similar to that of p-n junction, this is the depletion width. Okay, this particular forms the depletion width. And this is then, I should say, I should show this arrow in the opposite direction of the axis because this is a negative charge. So this is negative delta function, negative charges. Let's show it minus Q. So this is Q times ND. Okay, similar to that of what happens in a PN junction. So this is the depletion region of the MOS capacitor, of this MOS device, this particular device, metal oxide and semiconductor. So you have depleted it. Now what happens again? you go on increasing the negative bias. When you go on increasing the negative bias, let me take this particular thing here. Let me duplicate it and let me move it here. Okay, it will fit here. So when you go on increasing the negative bias, oh God, let me remove this thing also because I've explained it. Now what you do, you go on increasing the negative voltage. You go on increasing the negative voltage. Apply more negative voltage. Okay. What is going to happen? This is going to shift further. This particular Fermi level is going to go below the intrinsic level. Okay. Now it will look something like the Fermi levels are going to look something like this. The Fermi level is going to be here, but this particular thing, the bending will be so huge that it will look something like this. And there will be this particular bending will also increase. This will become something like this, something like this. Okay. Now there is a different picture. Now you have increased the negative bias, but because of the application of the positive biases now, what is going to happen is that excess of the holes are going to come up at this particular region now. They are the holes which will come up from the atoms because of they are going to come out from the atoms, or rather I should say you have taken so many number of electrons now that now the holes have or the vacant orbitals are started to come up or pile up near this particular region. So earlier you took those extra electrons. Now you are taking the electrons from the atoms itself. So you are kind of ionizing them more, and remaining thing left is the holes, and they are the ones that are going to remain at this particular region. So now the holes are going to pile up at this region. Okay, so now what is going to happen is that you draw the space charge diagram again. You already showed this particular thing as q times this is a positive charge q times nd. Now you have the holes are going to pile up at this particular region, apart from the acceptor type donors, impure donor non-immobile ions. And don't confuse this picture with the picture if you have a p type on this particular side in the semiconductor, that will have the opposite picture. Okay, don't confuse with it. We are taking here the n type right now, n type semiconductor. Maybe you might have seen about the p-type, but whatever happens in the p-type, opposite happens in the n-type. In the n-type, if there is a p-type of p-type, this particular semiconductor, you get the opposite bending, whatever you get in the n-type. Okay, you don't need to confuse yourself. So whenever the holes get accumulated at this particular region, the number of electrons or the electrons on the metallic side are going to increase minus q. And now you have the picture where you have a free holes here, you have the free electrons here, free electrons. Okay, now what's going to happen is that you have created a layer of carriers just beneath the oxide. Here you have created this layer of carriers. These are free carriers that is going to play a role in the electrostatic process. Okay, so basically these holes, they form a distribution from the surface, which is exponentially. If this is the surface, holes look something like this. They exponentially drop from the surface towards the bulk. And this particular length is called as dB length. Okay, this is called as dB length, which gives you the screening of the electric field. What is screening? What I mean to say is that you know that earlier there were positive charges, there were negative charges. The electric field was in this direction. Okay, and now again the electric field will be in this direction, but it will be dominated also by the component coming from the holes, because hole we treat as a positive charge, electron as a negative charge. So whatever the field is going to come from the positive charge, that is going to terminate on the negative charges. And inside the metal, there won't be any field, at least up to the skin depth. That means if this is the metallic side, this is the metal, the electric field won't be present here. Okay, it will be present in the oxide here. It will be constant inside the oxide, but it will just then decay inside the metal up to the skin depth. Skin depth is the depth up to which the electromagnetic field or electric field penetrates inside the metal. Okay, it's not present inside the metal. It's just very small depth of the order of maybe nanometers or few. Now, what happens is that if you now let's consider a p-type. Let's consider the opposite scenario. Let's consider the opposite scenario. Maybe we can check the whatever the question they have given. Maybe that might have a similar type of scenario. Hmm, which configuration is given in the questions? Okay, let me check here. Hmm. Okay, n-type. Okay, it's a similar question. Yeah, it's a similar question. Okay, so we are going correctly. So now what is going to happen is that this particular scenario now, if you have understood, then you have to go with the same strategy of computing the electric field. You know the charges as a function of x. You can compute the electric field as a function of x by integrating the space charge with respect to x from x1 to x2. And if you remember my previous the tricks I used, you can easily compute the electric field in this particular system. If you consider, let's say, the whole distribution as a almost like a delta function, and these particular positive charges as the spreaded uniform distribution, then you know how the electric field is going to look like. You just have to integrate these particular functions. Okay, so that will be actually dealt in the problems which you have been given in the assignment sections. But another thing is that now, just I want to finish with it. What you are going to do with these carriers? What to do with these carriers? What to do with these carriers? Okay, now we have the carriers near the surface. What we are going to do? Why is it useful to us? Because they are going to stay there. They are not going to move to the other side because there is an oxide between. Okay, it is like you have a oxide, and you have you have made so many kind of carriers at this particular place, and there are electrons at this particular place. This is metal, this is oxide, this is semiconductor. Now what you are going to do with this? Anyways, the carriers are not going to move through the oxide. It's not going to happen because oxide is a dielectric. It's not a conductor, it's an insulator. So what happens is basically is that this particular system is used to test how a particular device is going to respond under varying conditions. What do I mean to say is that this particular structure, MOS, it's like a capacitor where there's an oxide. This is metallic. This particular thing is metallic plate. This is the semiconductor system. You had induced the holes if you consider an n-type, and you have the electrons here. This is like a capacitor. You can model it as a capacitor, where the capacitance is epsilon A divided by D, where this is epsilon oxide. Epsilon oxide. Okay, this is the area of the plates. This is the distance between the metal and the semiconductor. That means this is actually the thickness of the oxide. Similar, the simple electrostatic problem. Now, whenever you give any particular signal here at the metal side, let's say you connected a negative and you connected a positive, you're going to see how the charges are going to respond in this particular system, how these particular charges will respond, and what are the complications that can arise. Okay, now when you induced these charges, if you understood this particular system, you can simply go on and understand the full-fledged MOSFET, which is the metal oxide semiconductor field effect transistor. You just have to do one thing. You just have to, I should say, connect a source and the drain. That's it. Earlier you had let me, if you take this particular device, you rotate or invert it by 90 degrees in the clockwise fashion, you get metal, you get oxide, you get semiconductor. This is the oxide. And you have the carriers here. You have the carriers here, free carriers. Now what you just do, you connect a region here and here. This is source, this is drain, and you get a full-fledged, this is the MOSFET. That's it. That's why you guys study about the MOS system, because this is the core block of the MOSFET. If you understood what happens in MOS, you can at least, I should say, the 50% of the job is done of understanding what happens in a transistor. This is the particular core block of this MOS. Then you connect this to up some particular voltage, let's say negative voltage. You connect it to the substrate also. You ground everything. You connect this to a particular positive voltage source. You ground it also. Then you give your signal at this particular, which is the gate voltage. This is the circuit of the MOSFET. And this particular system is represented by a symbol like this, like this. This is the VDD, the drain voltage. This is the source. This is the source terminal. This is the drain terminal. And if the current is flowing in this direction, you can represent the drain current, something like this. And you compute the output. This is the output voltage. This is the gate voltage. This is the circuit representation of this particular system. So you see where we started and where we ended. We started with just basic atoms and we ended at a circuit representation of this particular picture. And that's why this step-by-step approach is necessary, because you need to understand now, you need to understand what happens in this particular circuit, because this is a, we are all electrical engineers mostly. So we need to understand what happens at a circuit level, because we need to make those processors and chips, whatever is controlling your mobile phones and all of your electronic equipments. So this is the fundamental block, what is controlling all of the processors, your mobile phones and whatever you are using. And now this particular thing has, uh, I should say, I should say billions of this, billions of this are present in your processor. These are the fundamental blocks. Okay, approximately I should say 50 billion of these transistors are present right now, which are continuously switching on and off, and producing those, I should say, digital logic levels, or producing this data right now, what we are feeding. And that is basically the fascinating thing. And you see that this particular block now is just I will just finish with it and then we will start with the questions. Where this particular block is used is, now you up to this point you had a device level concept. Now this is the work of the device engineers. They, I should say, they make sure how to get to this particular point from this, and how does this function efficiently without any breakage. Okay, just a layman level right now I'm talking about. But after this, there is a job of the circuit designer to assemble these particular MOSFETs, single units, into a circuit, and to utilize it in such a way that it does a particular task. Just a basic representation. If you have this particular MOSFET, this single MOSFET, which I showed, this is the drain voltage, this is the source voltage, this is the gate terminal. Why are these two plates shown like this and not there's a space between it? Because in between this there's a dielectric. So that's why these two plates are not shown connected in the representation. Okay, don't get confused with it. You don't. You don't connect these two plates in the symbol because there's an oxide between. It shows that there is a field effect transistor. This is a field effect transistor. What it means is that whatever the field you are applying, that is inducing certain things here because of the electric field, not because of direct coupling. It's an indirect coupling because of electrostatic field generated because of the charges. The charge does not flow in this direction. Okay, ideally, because there's an oxide present here. Okay, so that is the actual representation of this particular schematic. Now, what happens is that from the device level, you go on to now a circuit level. And what you do in the circuit level is you connect these transistors, I should say, in a weird configurations, and you form something called as gates. Maybe you might know about logic gates. This logic gates are formed because of this transistors. So you combine these transistors and you make logic gates. Those logic gates you might know AND gate, OR gate, NAND gate, XOR gate. These are the things you know from the maybe the digital electronics or computer science. You use these particular types of gates in order to understand the Boolean algebra. What happens? Let's say if you have a NOT gate, you represent it something like this. If you give NOT gate a positive signal, you get a zero. You give it a zero, you get a one. This is the schematic of a NOT gate. But have you ever wondered what is inside this particular gate? What is inside this triangle? This is inside this particular triangle. Okay, so you connect it like, let's say, you connect a transistor in this fashion. This is a PMOS, this is an NMOS. From the previous lectures, you know what PMOS and NMOS is. This is VDD, this is source, grounded, this is gate voltage. Both of the terminals of the gate are connected here. And this particular system is something called as CMOS. CMOS means complementary. Complementary. Complementary means opposite of each other. Opposite of each other. What is opposite of each other? PMOS and NMOS. Two different MOSes are used here. Okay. And this particular system behaves as a NOT gate. That means if you give a positive signal here and you compute the output at this particular level, V output, you get a zero signal here. You give a zero signal here, you get a positive signal here. This is what is inside the gate. This particular symbol, this is what is inside it. So now you connect it in any weird combinations, you get all of those gates. You connect it like this, maybe somewhat like okay, not like this. Okay, so like this, like this, connected, connected here, here, common VDD. This is another gate system. This is again the PMOS. This is NMOS. You combine the gate of this with this, the gate of this with this, you get another logic element. So now you have to play with it at a circuit level. This is dealt in the circuit course, not in this particular course. So this is maybe some VLSI circuit course, VLSI design course, or deals with this particular system. But you see that how we went from this particular thing to this particular thing. Now this is the thing. This is the fundamental block what controls everything inside the chip. You are going to give it any signal, it's going to get converted either to ones and zeros. And that's a different story how we interpret the one and a zero of a transistor. We are giving it an analog signal, a continuous signal in time, and we are interpreting it as a discretized signal. Okay, that is a different story. But this is the particular scenario how you arrive at a particular CMOS circuit level from this particular MOSFET. So I felt this is important to show you guys that where are you going to implement these particular carriers and how are you going to use this. Now you do all sort of things with these devices and you form the gates. All of the gates, maybe AND gate, OR gate, NOR gate, and from the gates you can, if you form the gates, they are the building blocks of your computers. The computers are working by this particular thing and you are ready to go. That is all what electrical engineers are doing right now, and they have been doing from a couple of years. At least, I should say, this is one part of what electrical people do. Now, okay, so a lot of details into it. Maybe we can just start the questions now because 1 hour left. So I think this particular problem, starting with the first problem right here, just give me a second. So it says that the charge configuration of an ideal MOS cap for applied voltage is given. We have to answer the following questions and note that the free carriers are represented in red. Okay, this is represented in red and blue, whereas the bound charges are represented in magenta color. Okay, all right. So this is the particular space charge diagram of a MOS. What I just showed you. This is a MOS, MOS. So they have made a space charge diagram of it, where this region is rho in per centimeter cube, and this region is X. So what they are showing is that there is a delta, almost like a delta charge here, which is minus Q, and there is a delta charge here, which is plus Q. And you know that this is a metal side. This is a metal side, and this is a semiconductor side. So first of all, you need to answer that what is the type of substrate used on this side, and what are the biasing conditions of the MOS cap. How are you going to conclude it? First, first thing is that you see that there are free charges here. Okay, in what scenario will the free charges be accumulated at the oxide semiconductor interface? And you see that there are free charges. Obviously, on the metal side, there are always going to be free charges. Okay, but one thing to note here is that the free charges where will be deposited on the metallic side only when you connect a positive here. Okay, that's the only scenario free charges will be positive free charges will be deposited on the metallic side. And obviously, if the positive is on this side, the negative has to be on this side. This is point number one. Now, what is going to happen? If you paid enough attention, you notice that earlier I showed you the, I should say, if there are free charges present here at this particular region, then it means that this particular region there is an accumulation of charges. Accumulation of charges. That means this is something called as accumulation region. There are regions like accumulation, depletion, and inversion. I think we did not talk about accumulation. My bad. But accumulation is when you have accumulated the free charges of that semiconducting system. Let's say you had a positive and excess electrons on this side. Let's say if these excess electrons get accumulated at this region, this is called as accumulation region. Okay. And why is this particular region not the depletion region or the other inversion region? The answer is because in depletion and inversion region, there will be a depleted charge also present here. That can either be positive or negative, depending on what type of uh, PMOS or NMOS is what type of MOS it is. But that is the main significant difference between an accumulation region and depletion region and inversion region. In these two regions, you have the depleted charges also, which are the immobile charges. Okay. If you don't see any sign of immobile charges in the figure, you just see the free charges, this is always going to be accumulation region. Okay, accumulation region. Oh God. This is always going to be accumulation region. Accumulation of what? Free charges. This can be now either negative charge, this can be positive charge. Okay, but here it is negative. Why? Because this particular system here is the n-type system. That's why there is accumulation of the same type of charges. Same type of, because there are excess electrons in the n side, so the same charges have accumulated near the surface. And when you draw the band diagram of this, it will look something like this. There'll be bending here, there'll be bending here, and the Fermi level of this will be down than that of uh, than that of this particular Fermi level. So it is excess electrons, more of the electrons here, and there are positive charges here. So these electrons, these are accumulated electrons, accumulated electrons. Okay, this is the accumulation region. Here it is n-type. Don't get confused between p and n-type. We continuously move from p to n-type and to p-type. But if you just understand one of the device in a better fashion, then you will be able to analyze it in p-type also. You just have to go back and forth. But the concept is that in accumulation region, whether it is n-type or p-type, in accumulation region, the free charges will be accumulated. If it is n-type, the free charges will be electrons. If it is p-type, the free charges will be holes, which will be accumulated. If the same question would have been the p-type, then the space charge diagram would have looked something like this. There would have been excess holes here, plus q, and there would have been excess electrons on this side, minus q. If this was a p-type in accumulation. Okay, so that's why this particular thing is the this is an n-type region, n substrate with the accumulation mode of regime. Okay, now when you go to the depletion mode, when you go to the depletion region, here if you have this, let me draw this table. If you have this n-type substrate, and this is oxide, and this is metal, you connected, let's say Vg is positive or Vg greater than 0, you get accumulation, and bending looks something like this. Accumulation of electrons, bending here. This is the accumulated electrons. There are negative charges here, positive charges here, sorry. Now you reverse it. Vg is negative. That means Vg less than 0. You deplete it. You deplete the charges just at the semiconductor oxide interface. How you do it? You get a bending in the opposite direction. Because you connected negative on this side, the Fermi level on the metal side will raise. Notice that this and this. These are this in this figure it's raised because you connected negative to the gate side. And you have a Fermi level close to the valence band, and you have positive ions here. Okay, this is depletion because there is a depleted charge here. Right now, there are no free charges at present at the semiconductor oxide interface. Now you go on increasing the negative charge. V is negative, but you increase it. Now the free charges will come into picture. The bending will be more again. The bending will be same, but the key scenario is that the Fermi level is now almost crosses the intrinsic level at this particular region. At this particular region. Okay. And you have the free charges and you have the immobile charges as well. That's why you represent this particular space charge as I should say as free charge assay, and there are excess electrons. You consider this is n-type. Don't get confused. And here the metal is something like this, Fermi level. It is raised much more above than this. Notice the levels of the metal. So these are the scenarios, these are the regions. Okay. And so let's move on to the next question now, what the next question says. So the next question says that the field profile resulting from the above charge configuration and the corresponding band diagram. Now we have to make the field distribution. how the field represents, how is the field represented. You notice that there we have a free charge here, we have a free charge here. It is just like a parallel plate capacitor, just like a positive charge on this plate, negative free charge on this plate. The field only exists inside the that of a capacitor inside, and which is constant. And how does this come up? That's what we are going to see. You had a you had a positive charge here, you had a negative charge here, minus q, this is plus q. Now what you need to do, this is the space charge. If you integrate it with respect to x, you get the electric field. As simple as that. And if you remember, I have been telling you that if you have a delta charge, this is just like a delta charge. If you have a delta charge, you integrate it, you get a unit step. You integrate unit step, you get a ramp. You integrate ramp, you get parabolic. Now, what you have here is this scenario. That means this particular electric field of x is equivalent to some delta function of x divided by epsilon into dx. When you integrate it, you get unit step function of x by epsilon plus some constant. As simple as that. The unit step function is like this, constant. Okay, constant in what? In oxide, in this particular region. Okay, so you have to consider integrating from this to this region. But this is just like just a, I should say, the shortcut in understanding what happens if you don't want to go do the full mathematical derivation. So you get a constant field, and that obviously is comes from the electrostatics. If you have a positive charge here, you have a negative charge here. The field arises from the positive charge and ends at the negative charge. That's it. It does not penetrate into the semiconductor or into the metal. Obviously, inside the metal, it cannot exist. But this is the scenario if you considered, obviously, on the metal side, it will be a delta charge. But on the semiconductor side, you also considered a delta charge. But this is not what exactly happens. There is a spread of the charge present inside this particular system, something called as this particular spread. And this electric field can look like this, okay, slightly penetrating inside. But because most of the electrons are here, so they are going to shield the electric field. If there are positive charges, there are negative charges like this in this distribution fashion. Electric field coming from this will end at negative charge and at negative charge. So almost all of the, I should say, the shielding will be done by these negative charges. Okay, there will be electric field lines like this. There will be electric field lines like this. So that's why you consider the scenario, and the answer of this question is this particular thing. Now, on the other hand, if this would have been a case where there was, let's say, the same case, but there was depletion charge also present, that means this particular case. Or let's consider the inversion. If there was inversion, what would have happened? You would have got a, I should say, some particular charge here plus q. You would have got, if this is inverted, then there is a hole concentration basically here. Yeah, actually there is a hole concentration here because this was n type. It got inverted to p type. That's why this is called as inversion. So there is a positive and there is a hole concentration. Hmm. Am I confusing or am I just messing up things here? Just let me check. So let me talk about this particular scenario first. If there was a scenario that there was a positive charge on this particular side, and there was a space charge, depletion charge like this, depletion charge like this, depletion charge, a negative ions, and there were electrons present also. That means this is a scenario of inversion because both free charges and depletion charges are present. So this is inversion. Leave what type of MOS it is right now, whether it's PMOS or NMOS. just like a scenario, electrostatic scenario. What would have happened is that the electric field would have been like this, constant through oxide. Then, because these negative charges here would have shielded the electric field, because electric field wants to end at the negative charge. It would have looked something like this. Okay, there's basically a from this particular region, then this particular region. There's a drop at this particular point because because the electric field is almost shielded by this negative charge, free charges. And by the time it goes deeper into the depletion charge, which is also negative, it drops and it ends at this particular depletion charge bit, which is WD. This is the exact scenario if there would have been depletion charge. But if because there is no depletion charge, so the electric field is flat here, constant. Okay, so that might be maybe one more question here in this session. But and how do you and mathematically again you have to do the same exercise. Okay, because there was a if there would have been a depletion charge present, depletion charge, because this is uniform, like a uniform distribution. Okay, you could have represented as some u of x, let's say minus u of x. Let's forget about the sign right now. Then to this is rho of x. Then to compute the electric field, you have to integrate it. Integral of unit step of function, you get a ramp function, which is linear function of x. Linear function of x. And this is the linear function of x. As simple as that. Okay. So it again boils down to the same basic electrostatics used in the p-n junctions. Now, what you have is one important point is that will be, I think, covered in the next question. Yeah, we also had to answer the band diagram. So I told you that the for this question there was accumulation of these charges. Accumulation. That means there's a this particular system. This particular system. This is n-type, and there is accumulation of same type of carriers because n-type has positive and excess electrons. So these excess electrons get accumulated here. So that's why it is accumulation mode. And whenever you note this particular bending in the n-type, this acts like a well for the electrons, where the electrons can reside. This is just like a well in which the electrons reside. They like to stay there because it's a region of lower electrostatic potential energy. They don't have to spend a lot of energy to stay at this place because the electrostatic potential energy is lower. It has gone down at this particular point. So it's a well for electrons. Okay. And unlike this scenario, this is a this is huge electrostatic potential energy has increased at this position. That means electron cannot stay at this position. It does not like to stay at this position because electrostatic potential energy is higher. It needs to spend more energy to stay closer to this particular system. That's why this region acts as a well for holes or positive charges. It is considered holes here because it's ulta. Okay, hole likes to spend its, I should say, whole it likes to be there because of lower electrostatic potential energy for holes. Whatever happens for the electrons, the opposite happens for the holes. All right. So now moving on to another question. This is saying that procedure for drawing the PN band diagrams is similar to that of PN junction. So that you might have basically seen whatever we did in the PN junctions. That is a similar concept used in the drawing the band diagrams in the MOS systems. Okay, just give me a moment. Let me just charge this. If you guys have any questions, you can just ask. Okay, let's move forward. So this is a MOS capacitor again, and the band diagram is given. The first thing that you should note whenever the band diagram is given is the Fermi levels. You see the Fermi level of metal is higher than that of the Fermi level of semiconductor. It can only happen if you have connected some negative voltage here and positive voltage here. Because negative voltage raises the electrostatic potential energy of electrons, that is indicated by the Fermi level, and positive lowers it, indicated by the Fermi level. And this difference is the applied voltage. And note that the negative voltage is applied here. So it is basically minus 0.78 applied on the gate side. Okay, that means there are electrons here, and we are going to see what is going to happen at this interface. All right. So note here these differences have been given. The difference in the Fermi level in the bulk and the intrinsic semiconductor. That means EF minus EI is given as 0.29 eV, and EI minus EV is given as 0.56 eV. Okay, just for the sake of information. So first question is, the MOS cap is biased in which region? How are we going to denote this region? Now, going to the basics. This is an N-type. How do we know it? Because the Fermi level is close to the conduction band. And you have to look it outside the depletion region always whenever you look at the Fermi level in the MOS in this region. You have to look at this particular Fermi level here, not in this region directly. This is the bulk region. This is the surface near the oxide. So, so the Fermi level here is closer to the conduction band, indicating this is an N-type. Point number one. The next point, now it is N-type. You have connected negative here. You have connected positive here. What has it done? It has created a bending like this. It is as if the N-type was having positive ions and excess electrons. Those excess electrons have been taken away, deposited at the metallic side. Okay, and what it has done, it has made this system devoid of electrons. So only positive charges are left now. Okay, these are the depleted charges. That's why it's called as depletion. Depletion means you depleted or you made it less of something. You took away electrons from positive charges, you depleted it. So that is why this particular mode is the depletion region of the N-type, because you have depleted it. That's what it is showing. Now, there would have been another scenario. There is a one more important point. This particular Fermi level is just touching the intrinsic level at the surface. This is the key indication of the depletion region, because it is showing you that the this particular I should say EI in bulk minus EF, which was given basically 1 by Q, is it's equivalent to the something called as Fermi potential. This particular thing, the difference between these two in the bulk, it is the Fermi potential. But if you see, this difference at this particular point is zero. Okay, so whenever the Fermi level touches this particular intrinsic level, this is the key indication of the, I should say, the depletion region. Okay, at this particular point, if this Fermi level, or if the intrinsic region or the Fermi level goes below the intrinsic level, if the intrinsic level would have been like this is intrinsic, this is Fermi, this is this now the bluer one is the indication of the inversion. That means whenever this particular potential, which potential, let me just zoom this particular figure. It was like this, where this is the Fermi level and this is the intrinsic level. They are just touching each other. Okay, which is an indication of the depletion region. And now if it would have been the case that this is the Fermi level, this is the intrinsic level, then it would have meant that the potential near the surface, this difference and this difference basically, when the surface potential, this is the surface potential, when it becomes twice that of the Fermi potential was the difference between the EF minus EI in the bulk. When this becomes two times that of the Fermi potential, this is the inversion region. Okay. And the sign of this surface potential, whether it is positive or whether it is negative, it denotes the band bending. Whether the bands are bent upwards, whether the bands are bent downwards. That is what we are going to look in the next questions. But this is the concept of surface potential. Okay. It is the potential near the surface. Just like you had in all other cases, you could have defined the surface potential there also, maybe in Schottky junctions or other things. There were you also got the bending. So now you see that here's
Sir, wh-
yes, yes.
why have take minus 0.7878?
Sorry, are you saying
Sir,
anything?
why we have take minus 0.78? Uh, we can take plus. We can take positive sign.
No, like, yeah, good question. That is the point I was telling you. Because you see the Fermi level of this metallic side is greater than that of the semiconductor side. That can only happen if you have applied negative electrostatic potential on the metal side. Because this negative is going to raise the electrostatic potential energy of electrons on the side. That is only and that is the indication that Fermi level is up than that of semiconductor side. You got it? That means gate Vg is less than zero. Vg is negative, which has been applied. If this Fermi
Yes, sir.
level would have been here below that of the Fermi level of semiconductor, then Vg would have been positive. How positive, how much positive, that's a different story, but we're just talking about the magnitude. Okay. But because here the Fermi level is much above than that of the Fermi level of semiconductor, just like in a diode, just like you had a diode, in equilibrium, this is flat. If you apply the positive here, you apply the negative, that means you forward bias it. Okay. Positive की वजह से this goes down, this goes up. So it looks something like this. The Fermi level here, the Fermi level here. So यहाँ पे नेगेटिव अप्लाई किया था, Fermi level इस साइड से ऊपर गया. ये डिफरेंस जो है ये अप्लाइड वोल्टेज देता है. सेम कॉन्सेप्ट. यहाँ पे जो Fermi level है, this is above than that of this Fermi level. And it
Yes, sir.
means there is a negative voltage applied. Okay. So let's move
Okay,
on.
sir.
Now the other question. The charge configuration that approximately represents the MOS cap biasing is shown in the figure. Now for this particular biasing, the whatever is given in the questions, we have to look for the charge configuration. Now you know that I told you that this particular scenario is the depletion region because the Fermi level is just touching the intrinsic level just at the surface. So there is depleted, I should say, the charge is present near the surface. Okay, so what is going to happen is that this was the scenario. Let me just take it if I can just no, I don't think I can take it. Let me just draw it. You had the Fermi level of the metal here. You had the bending like this. This is the intrinsic level. This is the Fermi level just touching. You note that the drawing the band diagram is a art. I mean, you don't have to just draw it randomly. Everything should indicate something. Okay. So this is the conduction band. This is the conduction band. This is the valence band, and the Fermi level just touching the intrinsic level. And I showed you that there are positive immobile ions present here. There is a negative charge here. And how do you represent it, this such system? It is represented in a space charge diagram by positive charges here, which is Q times Nd, and the negative charges here, which is just like an impulse function, minus Q. And this is the particular scenario which it's shown. There are positive charges Q times Nd, and there is a negative electrons, free electrons present on the metallic side. So the part C is the answer of this question. As simple as that. Again, now you have to, now there is a scenario. If you have now this, you have to find the electric field. Electric field versus X. Again, you have unit step function of this. You integrate it to find the electric field. This is the electric field. How the electric field look like? It will be a ramp function. Okay, and inside the metallic system, you know the electric field cannot exist. So electric field is inside going to be constant. Now, what is the scenario that is exactly going to represent this particular thing? So you have this particular scene where you have the positive charge, you have the negative charge, impulse minus Q, Q times Nd. What you do, electric field will be in this direction, that is for sure, because electric field emanates from a positive charge. It starts from a positive charge, ends at a negative charge. Always. You cannot change the basic electrostatics. Electric field lines emit like this from a positive charge and end on a negative charge. Okay, so you draw it like this. You connect it like this. Okay, so electric field is in this direction. Now what is going to happen? How do you compute the electric field again? I told you this is the just like a unit step function. You integrate it, you get a ramp function. You integrate the unit step, you get a ramp function. And inside, on this particular side, you had a delta function. You integrate it, you get a unit step function. That means electric field is going to look like constant in this region, which is a unit step, and it's going to drop here, and it's going to be a ramp function at this particular place. Okay, so this is the particular scenario how you can compute this particular electric field. And now the sign of this particular electric field is going to be really important because the electric field is in this direction, in the opposite direction. That means this is the particular scenario. Now, this was in depletion region. If this would have been in inversion region, let us say, then you know that there would have been charges at this particular position also, holes, if this would have been inversion. Then how would have electric field look like? Was this would have looked like the same. There would have been a slightly parabolic type regime, then there would have been a drop. This would have been the behavior of the electric field, and this just comes again because from the equations. This is the scenario of the electric field. This particular thing is not the case here, and the other two are not also possible. This cannot even happen. This is electric field cannot abruptly change the sign. Okay, from the positive to the negative. This cannot happen. All right, so just basic concepts, and let's move on to, yes, this is a very good question. Now, when you compute the electric field, basically there are certain conditions which are applied at this interface. If you remember my lecture first where I showed the capacitor and a dielectric present inside the capacitor, this is dielectric epsilon 1, epsilon 2. These are two dielectrics. This is dielectric 1, this is dielectric 2. You need to consider this interface. What happens at this interface? You need to conserve something called as electric displacement vector, which is epsilon times the electric field on both of sides. Particularly if there is an electric field if there is positive charge here, there is negative charge here. The electric field lines are going to look something like this externally. But internally, how they are going to behave depends upon what is the value of epsilon 1 and epsilon 2. It may look something like this. Okay. And what governs it is the value at this particular point, interface. What happens at interface? Because of the something called as Maxwell's boundary condition, at this particular dielectric interface and dielectric semiconductor interface as well, or any other interface, the component of electric displacement vector, or the product of epsilon 1 and electric field on one side, should be equivalent to the product of epsilon 2 and electric field on the other side. Basically, these are the perpendicular components. That means the normal components of electric field multiplied by the permittivity on this side should be equivalent to the normal component of electric field on the other side times the electrical permittivity. This is the Maxwell's boundary condition. It means it represents the continuity of the electric displacement vector. You cannot break the electric displacement vector all of a sudden, okay, at the interface. There has to be the continuity of these electric fields, particularly this particular perpendicular component. There are other boundary conditions as well. The parallel component of the electric field, then there is perpendicular component of magnetic field and parallel component of magnetic field. But because you are not dealing with the magnetic fields here, uh, and uh, and also the parallel components, let's ignore them for a moment here. But this is the particular boundary condition which you are going to use. That means if you have this metal semiconductor interface at this particular interface, because this oxide is having epsilon oxide and semiconductor is having epsilon silicon, the permittivity. Now, what is this permittivity? Permittivity is medium's response to the applied external electric field. That is the simple definition of permittivity. That means if you are giving some input, you are getting some output. Let's say you have a black box. You are giving some input, you are getting output, input. This black box has some function. Let's call it T. Then the output would be some T times the input, because there will be some change here at the output. So this particular T is basically the electrical permittivity. So it governs that how the field is going to look like. So if you give some field, electric field, you get output as D vector, which is the displacement, electric displacement vector. And what governs its conversion is epsilon, the permittivity. That's why you write D equals to epsilon times electric field. This particular thing governs its response to the external electric field. And it is basically a matrix, not a single value. Okay. It is different in different directions. If you have a three-dimensional medium with, let's say, y, x, and z, then actually epsilon is something called as tensor. Let's not go into that detail, but it's represented as epsilon xx, epsilon yy, epsilon zz, epsilon xy, epsilon xz, so on and so forth. You can fill the loop gaps. Epsilon yx, epsilon yz, epsilon zx, epsilon zy. This is the actual, I should say, the permittivity matrix of a three-dimensional system, because permittivity is different in different directions. Okay, but you, for the first order approximation, whatever you study, this is also applicable. You can consider this particular thing, but it governs the response of the medium to the external electric field. So that is why whatever is going to happen on one side of the interface is going to be, or the electric field, the normal component of electric field is going to be continuous at this point. That means epsilon ox electric field in oxide is going to be equivalent to epsilon silicon electric field in silicon. This is the particular boundary condition which is used. That is this particular question is about. The field in the oxide is dash the at the silicon dioxide interface. So this is epsilon ox. Electric field inside is E ox, which we saw it is constant, but we don't care about the values right now. We have to talk about the magnitudes. And in here it is epsilon silicon times the electric field in silicon. These two are equal. Where? At this particular interface. These are not equal everywhere. This is the interface boundary conditions. Where do you apply the boundary conditions? Whenever you have a boundary comprising of two different materials. Interface. Okay. बिकॉज इंसुलेटर में जो एटम्स है वो सेमीकंडक्टर के एटम्स से स्पेसिंग के आई शुड से इन टर्म्स ऑफ स्पेसिंग दे आर डिफरेंट ओके दे आर नॉट सिमिलर टू दैट ऑफ सिलिकॉन so that's why whenever you will apply the external electric field they will respond differently to the external electric field and that is governed by electric displacement vector. So basically d1 is equivalent to d on the oxide should be equivalent to d on the silicon electric displacement vector. So this comes from this. Electric displacement vector is epsilon times E. It is similar to that of magnetic field. Magnetic field is basically mu naught times the magnetic field intensity, applied magnetic field. This is the magnetic field vector is basically the permeability times the applied magnetic field. Similar concept. Okay, this determines how the medium will respond to the external magnetic field. This determines how the medium will respond to the external electric field. So using this condition, now you know the epsilon ox and epsilon silicon values. I guess that those have been given in the question. Let me just check. Epsilon silicon is 12. Let's take it 12. Epsilon silicon dioxide is 4. Let's take it 4. Okay. So epsilon silicon, this is silicon dioxide, oxide. It is 4 and silicon is 12. Let me just cross check. Yes, it is 4 and 12. And that means now you can compute the ratio. Epsilon ox, E ox is equivalent to epsilon silicon, E silicon. That means E ox by E silicon is epsilon silicon by epsilon ox. This is 12 over 4, 4, 1, 4, 3 are. That means epsilon ox is equivalent to 3 times the epsilon silicon. Okay, so this is the answer of this question. That means the electric field in the oxide is going to be 3 times that in the silicon. That is why when you saw this drop here, you didn't question why there is a drop because this field is 3 times that of this field. That's why there is a drop of this particular because this magnitude is 3 times electric field in the silicon. This magnitude. Okay, this is the E in silicon. This is the E in oxide. And E in oxide is 3 times that in E in silicon, the magnitude of the electric field. And interface के पास क्या हो जाता है कि it drops because of the interfacial phenomena and because of the boundary condition you have used. Okay, the magnitude of the electric field overall in oxide is greater than that in the silicon. That's why there's a drop in particular shown in the electric field. Okay. So now moving on to another problem. Now there is a question of doping concentration in silicon and the I should say the electron concentration at the silicon dioxide interface are given by dash and dash. You see that this particular reflectant, remember, is also saying the same thing. That electric field is basically discontinuous at this particular point, and it drops because the electric field on inside the oxide, silicon dioxide, is greater than that at the silicon. Okay, and the normal component means the perpendicular component of the displacement field vector, which is the D, is continuous across the interface. That is the same thing. Now, moving on to the question 7, the doping concentration in semiconductor and electron concentration at this interface are given by how are you going to compute the doping concentration? Okay, we are given all the details. We are given EF minus EI, which is something called as Fermi potential. This is called as Fermi potential. Fermi potential. The difference between the Fermi level and the intrinsic level in the bulk. This is bulk. Up to this region, it's called bulk. This is the surface or the interface region. This region is bulk. And We are given everything. Basically, this Fermi potential, you know from the basic, again, the diode physics. This can be written as kT by q ln of Nd divided by Ni, the difference between the Fermi level and the intrinsic level. And you are given everything. I think the difference you are given, you have to compute the concentration Nd. And this is a simple cakewalk question now, just a maths. You can write it as EF minus EI Q by KT exponential ND divided by Ni. You got ND. ND is equivalent to Ni times e to the power Q EF minus EI divided by KT. As simple as that. And everything is given. Just have to put the values. And what is the next part you have to find is the what else? What is find? The doping. We have found the doping. This is in the bulk. This is in the bulk. Remember, this is in the bulk in this region. Here the concentration will be different now because of the bending. सब मतलब जो सरफेस पे सिनेरियो चेंज हो जाता है क्योंकि फर्मी लेवल एंड इंट्रिंसिक लेवल के बिटवीन जो डिस्टेंस है दैट हैज आल्सो चेंज्ड हियर it remained constant in the bulk, but as you move towards the surface it changes. Okay, now the we have to find the doping, the concentration here. How are you going to find the concentration? Because you know the surface potential is basically the difference in the difference in the, I should say, the Fermi level in the bulk and at the interface, or I should say the difference in the intrinsic level in the bulk and that of the interface. That means the, I should say the, do we have to find the silicon dioxide interface? Whatever is the intrinsic level in the bulk and whatever it is in the interface, this is going to give you the phi s basically. And using the same logic, then again you can, I should say, you can obtain the particular value for the surface potential. I guess that is for the next part. But for this part, what we were supposed to compute. I'm confused. Doping concentration in the semiconductor and electron concentration at the silicon dioxide interface are given by. Okay. Okay, so doping concentration in semiconductor and electron concentration at interface. Is there any error? We have found I think the answer of this question is 1.1 into 10 to the power 15 and 10 to the power 10. Oh, yes, we forgot the main thing. So this is the surface potential. This is the next question. You computed this particular thing for the bulk, and what will be the concentration here? Because Fermi level is equivalent to intrinsic level. Whenever you have a semiconductor where there is the intrinsic level in the middle, that is the Fermi level. This is basically something called an intrinsic semiconductor. And you know intrinsic semiconductor mein n equals to p equals to ni square. Okay. Or I should say the product n dot p equals to ni square. The concentration is basically ni, which is the intrinsic concentration, 10 to the power 10 per centimeter cube. Simple, as simple as that. Because at this particular region, the Fermi level and the intrinsic level are same now. So the concentration is going to be that of the intrinsic concentration, whatever was the background concentration of the particular semiconductor. So that's what we have found. That is 10 to the power 10. Okay, I just got a little bit confused in it. Now, let me check this timing. Now, what next? The surface potential. The surface potential we have done again. The surface potential is the difference in the intrinsic level in the bulk, and that is at the particular interface, which is going to be equivalent to minus 0.29. So that is the particular surface potential. Okay. And You can basically compute it also from let's say whatever you basically the surface potential sign is going to be important. Whenever you have the surface potential, either it will be negative, either it will be positive. So if it is like negative, then you and if the and semiconductor is n-type, the bands are going to be bent upwards. If it is positive, the bands are going to be bent downwards. And if the surface potential is negative and positive, and if it's a p-type, then for the negative case, it's going to be bent downwards. For the positive case, it's going to be bent upwards. This is the convention used for the surface potential. Okay, just to give you a rough overview of it. And what else? What else is there? Yeah, this thing I think I covered initially that the from depletion to inversion region, it gets changed whenever the surface potential is two times the Fermi potential. That means the Fermi level crosses this intrinsic level. This is intrinsic level, this is Fermi level. And this particular thing becomes two times that of Fermi potential. This is Fermi potential. Why two times? Because it is just like this. Two times that of the Fermi potential. Phi F, Phi F. So surface potential is two times that of Phi F. Okay. Now the gate voltage applied. This also I showed. The gate voltage is this, but it is negative because Fermi level is gone up than the Fermi level in the semiconductor. So it is the negative voltage is the gate voltage, and you have to compute the drop across the oxide. Okay, now this is an interesting problem. Whatever you gate voltage you applied is going to drop across the oxide and across the semiconductor. In across the semiconductor, where does it drop? At this particular surface. What do you call as surface potential? It is just like Ohm's law. You apply some voltage, there is some drop. These are just like resistors. Okay. Now you have to compute the overall voltage. Whatever the gate voltage you applied gets dropped at the oxide plus the semiconductor. Oxide plus the in semiconductor it gets dropped at the surface. Okay, because there is a bending at just near the surface. Now what you have to compute is the you have to compute the drop across the oxide. That means you have to compute Vox. That will be gate voltage minus the surface potential. Now here the sign is going to be really important. The gate voltage is negative and the surface potential initially which we computed was also negative of 0.29. So it's minus 0.78 plus 0.29. So it is minus 0.49 volt. That's why this you have to take care of the sign here. You cannot mess with the signs. Okay. That's why this sign is also important. Otherwise, you're going to get the wrong value of the oxide. That means this much voltage is going to drop across the oxide. Out of 0.78, 0.49 volt is going to drop across the oxide. The huge drop. It is just like you have a battery, you connect it to a resistor, and you connect it another resistor. This is the resistor R1, R2. This is this is the oxide, this is the semiconductor. So the most of the drop is across this resistor. Okay. That means
Sir,
R1 resistance is much greater than resistance R2. Oops, sorry. Yeah, say it. Just turn off
sir,
this.
0.29, sir,
Yeah, yeah, yeah.
below the Fermi level, below the
Mm-hmm.
Fermi level.
Hmm.
So there will be uh, um, minus sign, positive sign,
Yeah, there'll
minus sign,
be
or
yeah, there'll be negative sign because it is just let me just share the screen.
but
Okay.
0.78, sir,
Hmm.
uh, upper the upper the uh, Fermi level. So
Uh,
there is minus
no,
0.78.
I don't get your question exactly. So what I mean to say is that the gate voltage is going to be negative, and that is reflected here, and the surface potential is also negative. That's why you have the negative here. That's why negative and negative becomes positive, and you get the overall sign is negative. Minus 0.78 plus 0.29, and you get overall voltage. The voltage drop across the oxide is minus 0.49. The sign is going to be important. Okay.
Sir, 0.78 minus 0.78, it is upper the Fermi level.
I don't get your question exactly. Okay, can you just say it in
Fermi,
Hindi? If you're comfortable in Hindi, just say it.
सर फार्मी लेवल का ऊपर है 0.78
Mm-hmm. Mm-hmm.
और फार्मी लेवल का नीचे है 0.29 तो
Hmm. That is the
फार्मी
that
लेवल
is the
से
that is this is the Fermi potential. This is the inbuilt. You are not giving it. Whatever you are giving is the difference between this Fermi level in the metal and the Fermi level in the semiconductor. This thing. This is the V applied. Okay.
ओके सर
और ये जो V applied है ये ड्रॉप हो रहा है ऑक्साइड में एंड सेमीकंडक्टर में जस्ट लाइक अ रेजिस्टर्स दो रेजिस्टर्स है एक इंसुलेटर है एक मतलब ऑक्साइड है दूसरा सेमीकंडक्टर है सेमीकंडक्टर का जो सरफेस पोटेंशियल है तो जस्ट लाइक टू रेजिस्टर्स whatever you are that means you are applying let me draw this in a better way you are applying negative here positive here you are applying minus 0.78 you are applying minus 0.78 here उसमें से minus 0.49 volt is dropping here and the rest is dropping here you can compute now how much is the rest okay so that is the actual scenario the potential drop just like kvl normal you have to conserve the voltage you have to apply the kirchhoff's voltage law how much voltage drop will be across this how much voltage drop will be across this and when you go on forward when you move on in this course you are going to get more terms whatever the gate voltage you apply that drops across the oxide that drops across the surface semiconductor surface and that also drops in maintaining something called as flat band this comes because if there are maybe if there is a difference in the Fermi level, a difference in the work functions of the metals and the semiconductors, and if there are fixed charges present inside the oxide. Okay, so Q is C times V, and you can get V as this times C ox. Okay, जैसे if you move on in this course, you are going to get equation like this. This is the equation of the
दिस में
voltage drop.
दिस
Okay.
मीन्स वी अप्लाई माइनस 0.78 वोल्ट
Hmm, exactly. Whatever you apply is going to drop across these terms, these components. Just like in KVL,
यस
these are just like resistors. This is one resistor,
यस
this is
सर
one
यस सर
resistor, this is one resistor. ठीक है? And ये वाला component maybe you will deal with in the next. This is
सर
this
दिस इज
comes in
गिवन सर
what is
दिस
given?
इज गिवन सर माइनस 0.78
This is given. This is VG. This is the applied voltage.
यस
This ये battery से
यस
आता है.
सर
That gets dropped across the resistors. As simple as that. I think we spend a lot of time in this question. Let's move on to the next question. And this is I should say the easiest question of this. Just like the depletion width of the diode, you have twice epsilon by Q, 1 by ND, because you don't have Na here, times the surface potential now here, instead of the built-in potential. Just like a built-in potential concept in the diodes, you have the surface potential concept here. There you considered, in the diode, you considered this as the built-in potential. In the MOS, you consider this as a surface potential. As simple as that. That's the simplest explanation. Okay. Now you have to compute this thing. Everything has been given. I think surface potential you computed 0.29. Okay. Now you don't put the negative sign here because this is the magnitude. This is the magnitude of surface potential. Remember that. The surface potential is negative, but the magnitude of surface potential is going to be 0.29. If you put the negative value here, it's going to blow up. It's going to give the imaginary width, which is not possible. The depletion width has to be positive real quantity. And if you put the values, you get as 0.586. Everything has been given, just a calculation needed. But make sure this is the magnitude of surface potential. And as you go, you will look in the inversion region. This depletion width basically is given by twice epsilon by q 1 by nd times the 2 times the Fermi potential. This is basically the surface potential equals to 2 times Fermi potential in the inversion. When the MOS just goes from depletion region to the inversion region, you replace this particular term by this thing and you compute the depletion width. Okay. And this is the maximum depletion width you can reach. You cannot go beyond it. There are certain reasons. We'll talk about it in the next session. But let's close this session earlier today because I was not feeling well. Let me just ask if you guys have any questions or not. Then we can maybe end this session. Okay, so what we have covered is okay. So let me just stop this right.